Hi everybody, my name is Trevor Asaf. I'm here today with Nick Dard and Kyle White. We are Team A9, and we're here today to talk to you about the Pigeonhole Principle. Now this is a relatively simple concept, and it is especially easy to picture. Imagine you have 10 CDs, but only 9 cases. No matter how you try to arrange the CDs, there will always be one case with more than one CD in it. Now the formal theory is as follows. If k is a positive integer, and k plus 1 or more objects are placed into k boxes, then there is at least one box containing 2 or more of the objects. Let's inspect an example. If 8 people are born in the same week, at least 2 must share a birthday because there are only 7 options. So in this case, let us assume that the 8 people are the objects, and the 7 days of the week are the boxes. So if we have 8 objects, and we want to put them into 7 boxes, we can proceed as follows. Let's put the first person in Sunday, the second person in Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So now we have 7 people, 7 of the 8 people in 7 boxes. We have one person left over, one X to place into one of these boxes. It can go in Sunday, Monday, Tuesday. It can go in any of these days, any of these boxes. But as we can see, no matter what box we put it in, no matter what day we assign the birthday of this lone X, it will overlap with the birthday of another X. And in this way, this is a visual representation of the formal theory of the Pigeonhole Principle. And a corollary of this idea is, if a function f is a set with k plus 1 or more elements, to a set with k elements, it is not one-to-one. So next we're going to introduce a branch of the Pigeonhole Principle called the Generalized Pigeonhole Principle. And the theorem is as follows. If n objects are placed into k boxes, then there is at least one box that contains n over k, the floor of n over k actually, the floor of n over k objects. Now let's consider an example to get a better handle on this new concept. So how many selections are necessary to pick a marble of the same color twice if there is a bag with 5 different colored marbles in it, where the marbles are replaced after each selection? Great, now if we look back at the theorem we just learned, the generalized pigeonhole principle, we can use the equation in the theorem to construct our answers. So the answer is n, where n is the number of objects, over 5, where 5 is the number of bags. The ceiling of that, excuse my malapropism earlier, I just realized that earlier I said that these brackets were the floor of n over k, where in fact they refer to the ceiling of n over k. Pardon me. So the ceiling of n over 5 equals 2, where 2 refers to the number of objects that we are ultimately trying to acquire. This first occurs when n is greater than 5. This expression right here will equal 2 when n is any integer, any value greater than 5. So n can only be a whole number, so n will be 6. N equals 6 is our answer. The minimum number of selections. Great. Next example. Okay, during a 30-day month, a team plays at least a game a day, but no more than 45 games. Show that there must be a period of some number of days consecutively during which the team must play exactly 14 games. Great. So let's say that A sub j is the number of games played by this particular team on the jth day of the month. Oh yeah, I forgot to say, the month is restricted at 30 days, so no more, no less than 30 days, to make things simpler. Great. So A sub j is the number of games played on the jth day of the month, And now we have a sequence. So we can say a sub 1, comma a sub 2, comma dot dot dot, a sub 30. These are all, each value, each element in our list corresponds to the number of days, or number of games played on the day denoted by the subscript. Okay. Now we know, because of the restrictions above, that 1 is less than or equal to a sub j, which is less than or equal to 45. Now if this is the case, we have an inequality equation, so we can add an integer to both sides, or to all of the sides actually. There are 3. Now if we add 14, we get that 15 is less than or equal to, let's have a new, or a sub j plus 14 is less than or equal to 59. Now we can rewrite our sequence of a sub j's as follows: a sub 1 plus 14, a sub 2 plus 14, comma dot dot dot, a sub 30 plus 14. It's the same sequence, just we added an integer to it. We added 14. Now we have an interesting event just occurred. We generated 2 sequences, each containing 30 integers. And we know the first one is less than or equal to 45, and the second one is less than or equal to 59. So we can assume, or actually we can deduce, that both sequences, a sub j is less than 59, less than or equal to 59, and a sub I. Let's assign a sub I to a sub j plus 14. I don't think we did that. No, we did not. No, we don't. So this is a sub I. A sub I. So a sub j is less than or equal to 59, and a sub I is also less than or equal to 59. So we know that there are 30 integers in the a sub j sequence, and there are 30 integers in the a sub I sequence. So total, we have 60 integers. However, they all have to be between 1 and 59. So we have 60 integers to place in 59 slots. So 60 objects, 59 bags. You know at least 2 of those objects, 2 of those numbers are going to be identical. And that is the crux of this problem. Therefore, by Pigeonhole Principle, at least 2 integers in our 2 sets must be equal. By Pigeonhole Principle, we know that because there are 60 objects and only 59 boxes, that there must exist some AI that equals some AJ plus 14. This means that exactly 14 games were played from day J plus 1 through day I. Thank you for your time. Again, we are Team A9. This has been a presentation on the Pigeonhole Principle and its applications. See you next time.